Well, thanks everyone for coming out on a perfectly otherwise good Wednesday evening. And I'll apologize up front for what you're going to hear. I'm a physicist with Utah Climate Center. I've been doing communication in climate change and sustainability science for about the last decade or so. I intended to be doing it for about a year, and then it turned into another year, and then it just took on a life of its own. And so here we are 10 years later, and I'm still doing that, and I've yet to get back to my lab. I don't think that's going to happen now. I bring that up because I always start with this slide. If this is how you feel when the topic is climate change, you have every right to feel this way, and you're certainly not alone. There's a tremendous amount of confusing and conflicting information in the media about the science of climate change, about the public issue of climate change. And so over the next 30 or 40 minutes, we're going to try to clear some of that confusion away. And I would also like to say that understanding Earth's incredibly complex climate system to the level that we do really does stand as one of humanity's great scientific achievements. To understand the climate system to the level that we do, you have to study a very broad spectrum of science. Physics, chemistry, biology, ecology, certainly, and then dozens upon dozens upon dozens of sub-disciplines of those. So climate science is really at the pinnacle of our sort of pyramid of scientific understanding. It really is a truly incredible achievement to know as much as we do. That said, and you're not meant to be able to read all of these. This is just all, and just a small sampling of sub-disciplines that publish papers on climate change and which need to be synthesized through a lens of climate to understand the system. But that said, understanding the science of the climate system is a small task relative to understanding the science of climate change. And certainly, the physical science of climate is a piece of climate change, but it's not the biggest piece. There is the science of impacts to nature, to natural system, impacts to human systems, and lots of sub-disciplines within. The science of mitigating these changes and the science of adapting to these changes, and much of this science is what I call the harder sciences as opposed to the hard sciences, the harder sciences of social sciences. So mitigation, adaptation is a lot of sociology, it's a lot of politics, it's a lot of history, it's a lot of economics, the dismal sciences, people call that one. It's just an enormous topic. And there's not a single facet of our society that isn't touched by this. We'll come back to that in a moment. But there's a lot to understand about this topic. That said, over the next 30 or 40 minutes, I'm going to just summarize for you 4 things that science knows with very high confidence about Earth's climate system. And the first thing that we know with high confidence is that the planet is warming globally. And this is what that warming looks like. From the end of the 19th century to the middle of the 20th century to today. So now as you watch the different locations on the map here change from the cooler blues to the warmer reds, you're watching those locations warm. So this is a map of temperature change, not temperature. The Arctic did not become warmer than the equator, but it is warming more. So we'll look at that one more time. From the end of the 19th century to the middle of the 20th to today. And what we notice from this data, this is a very rich data set, but 2 things are really quite immediate. One is that the entire planet is warming. And the second is that warming is not uniform. In particular, the high latitudes in the northern hemisphere are warming faster than the global average, and the land surfaces, the continents, are warming faster than the oceans. But that said, we can average it all up and say that as a whole, the planet has warmed an average of 1 degree Celsius over the last century or so. Most of that has come in the last half century. And for those of you who are metrically challenged, you can convert a change in temperature from Celsius to Fahrenheit by roughly doubling it. So that's almost a 2 degree Fahrenheit change. Now, we can do this sort of an averaging calculation, not just for the year 2015 over the last 100 years, but we can do it for every year going back 130 years or so, calculate a global average temperature relative to some baseline, a global average temperature change relative to some baseline. And when you do, it looks like this, starting in the late 19th century on the left, moving up to 2015 here on the right. And the baseline we're using is the mid-20th century. So we're measuring here global average temperature relative to the mid-20th century, just as a baseline. So we'll call that 0. And here, this change in temperature is quite obvious. From the much cooler years in the early 20th century to this continuous progression of record-setting years in the late 20th century, right up until today. Last year is the warmest year on record, breaking the previous record of 2014 by a long shot. And this year, 2016, is very likely to break that record, and is very likely to break that record again by a long shot. It's been an extremely warm year globally. So terminology-wise, this is what we mean by global warming. This is global warming. Okay. The second thing we know with high confidence is why the planet is warming. And not to put too fine a point on it, but it's because of us, human activities. There are a number of human activities that contribute to this, and I'm going to simplify just a little bit, but not too bad. Principally from human emissions of carbon dioxide, and we do that principally, but not exclusively, but principally from the burning of fossil fuels. And this is, as a result of these human carbon dioxide emissions, the carbon dioxide levels in the atmosphere have been rising for the last couple of hundred years since we've been burning fossil fuels in earnest. It's risen more than 50% in the last 250 years. More than most of that rise has come in just the last 50 years, which I've plotted here. We started 200 years ago at about 280 parts per million, and today we're just over 408 parts per million. So this is where we are. And this is important because carbon dioxide is a greenhouse gas. And greenhouse gases, like as many of you know, because of their molecular structures, are able to trap energy that's leaving the Earth in the form of light, principally infrared light. So it's not light that we can see, but it is light nevertheless. And these molecules trap that energy and convert that energy into thermal energy, heat. So they warm the atmosphere, and that warmth is then transmitted throughout the rest of the Earth system. So that's what greenhouse gases do. And it's this dramatic rise in greenhouse gases, particularly carbon dioxide. I'll give it just a second here. Principally carbon dioxide that's raising our temperatures. So Earth is warming principally because of us, because of human activities. The third thing we know with high confidence is that this human-driven global warming is disrupting the planetary climate system. And that's because in Earth's climate system, everything is connected. So if you change the temperature, you change everything else. So for example, yeah, that's how I feel too. So for example, we know that warmer air holds more moisture. So when you raise the temperature, evaporation goes up, and drier areas tend to get drier. At the same time, you've now put more water vapor into the atmosphere. You've evaporated more water. So when you do get a storm, the precipitation is more intense. And we see this pattern happening, documented very well over the last half century, all across the globe, on all continents, northern and southern hemisphere. And by itself, this intensification of the hydrologic cycle, intensified evaporation accompanied by intensified precipitation, is a significant impact to the Earth's climate system. But as I alluded to before, it's not the only one. In fact, it just scratches the surface. Because again, when you change the temperature, you change everything else. You start to melt the cryosphere, all the frozen bits on the planet. This is continental ice sheets of Iceland and Greenland and Antarctica. This is polar ice at the North Pole. That's frozen sea ice. This is mountain glaciers. This is tundra. This is even mid-latitude snowpack. You change whole weather patterns. Here in the mid-latitudes, the biggest driver of our storm tracks is the jet stream, and we're seeing changes in the jet stream that the physics predicts when you warm the atmosphere in the way that we're warming it. That changes where the storms occur and where they don't, how big the storms are, how intense they are. It changes whether it's rain or snow. This changes drought intensity, drought frequency, drought location. It changes many things about the soil chemistry. It changes ocean chemistry. It changes ocean currents and atmospheric circulation. It changes where things grow and where they don't. Everything changes. And so this then, going back to terminology, is what we mean by global climate change. So this anthropogenic global warming is driving a change to the entire planetary climate system. And of course, as you change the physical system of the climate, you change the entire biosphere, all the living bits on the planet. Lots of things are happening in the biosphere. Some of them, many of them pretty intensely. For example, species are migrating away from the equator, and toward the poles and upward in elevation as they try to maintain their preferred environment and temperature and climate. Life cycles are changing. When things go dormant, when they become active, when they migrate, etc. A piece of biology called phenology. And the biodiversity loss, which is kind of a fancy term for extinction rate, is going through the roof. Ecologists now tell us we're losing species off the planet at a rate somewhere between 500 and 1,000 times higher than what the background extinction rate is believed to be. Not all of that intensification of the biodiversity loss comes from climate change, but a significant portion of it does, and an increasing portion of it does. And then, of course, when you change the living system, you change the human system, which is completely immersed in the rest of the Earth system. There are now measurable impacts to all kinds of pieces of our global human civilization, our human systems, to the agricultural system, to the energy system. Human health is impacted, transportation is impacted, fisheries are impacted, political stabilities. 65 million people are now displaced around the world as refugees. A significant fraction of those directly or indirectly related to environmental change in their home, including the large changes that are happening across the Middle East, North Africa, and Europe. So we're already seeing significant impacts to human systems. In some places on the planet, these impacts have already been catastrophic. There are whole island nations that are now packing up and moving, tens of thousands of people, because they're, in the next several decades, their nations will essentially be uninhabitable as a result of rising sea levels. This is Lower Manhattan after Hurricane Sandy. I think it's clear when you look at something like this, we are just immersed in our environment. This is happening around Utah. Utah is warming, as evidenced by measurements all across the state. The blue bars there represent the warming trends in those locations around the state. As a whole, Utah is warming at about twice the global average. So we've now warmed almost 4 degrees Fahrenheit over the last century, most of that again coming in the last 40 or 50 years. There are places in southeastern Utah, Bluff, that are warming at close to 3 times the global average. And it is changing our climate, and it is having impacts. There are changes to, we're seeing a shift to not just higher average temperatures, but a real amplification of the extreme high temperatures. I'll come back to that in a moment. Springtime snowpack is declining across the state, measurably. We have impacts to the ecological system, for example, bark beetle infestations, which are changing whole forest ecosystems, and also playing into the world of bigger and hotter wildfires, which we see all throughout the West, in fact, all across the globe, with a fingerprint of climate change on them. I want to just look at these extreme high temperatures because we often get stuck talking about average temperatures, and this is, I think, one of the more visible areas where we can see how this affects us already. So Tooele happens to have a really nice long temperature record with very few missing data points, and so it makes a nice way to analyze this. This is true all across the state, but Tooele makes a particularly nice one to analyze, so I'll just show it to you here. What you're looking at here are summertime maximum temperatures in Tooele in the 1960s and how often you got a certain temperature. And what you see is the most common summertime high temperature in Tooele in the 1960s was right here, 91 degrees. So this is how many days did we get this particular temperature in the 1960s. So this is a histogram, a distribution of high temperatures. And you'll see that the most common one here was 91 degrees, and it never got above 100 degrees in Tooele in the 1960s. Here's that same distribution for the first decade of this century, the 2000s. And you can certainly see the whole thing is shifted over. So the average temperature has gone up a couple of degrees, in fact, about 3.5 degrees for Tooele. And so you can see here where there's the bright white, essentially, is there are more cooler days in the 1960s that they didn't have in the 2000s. The shaded area here is where there were more warmer days in the 2000s. So certainly the average temperature's gone up. I want to focus, though, on this high temperature tail for a moment. So what you're looking at now is a histogram of the number of days above 90 degrees for the different decades in the 20th century all the way through the first decade of this century. And so, and right in here, the 1960s is where modern global warming really kicks in. This is where the human tug on the climate system starts to overwhelm all of the natural tugs on the climate system. And as you see, that high temperature tail starts to increase monotonically, just more in the 80s and the 70s, more in the 90s and the 80s, et cetera. But it gets even more interesting as we go farther into that high temperature tail. So this is days above 95 degrees. And you see that starting to skyrocket here. Days above 100 degrees. So in the entire 20th century, there were 66 days above 100 degrees in Tooele. In the entire 20th century. In the first decade of this century, there were 94 such days. And then 101, 102, 103 degrees. 4 days above 103 in Tooele in the 20th century. 28 days so far in the first decade of this century. And it's this kind of impact that is particularly acute for biological systems. You can raise, if you get extreme temperatures, in some cases for even a few hours, can have an extreme impact on certain species. The cutthroat trout, I'm told by my ecologist friends, is one of these species extremely sensitive to, say, for example, warm water temperatures. And that can happen when you just have a few hours of these very extreme temperatures. Okay. No, sorry about that. I keep meaning to change that. It gives me a little vertigo every time I see that. Okay, so the fourth thing we know with high confidence then is that if we continue on our current pattern of warming, of climate change, it poses extreme risks for humans. And again, we know this with high confidence. And the reason I can say that is that this analysis comes from sort of two parallel tracks. The first track is that we use the impacts to the natural and human systems that we've already experienced based on the climate change that we've already experienced as a way to calibrate moving forward. And what has happened is, over the last decade, these impacts have, by and large, been significantly stronger than were expected even a decade ago for the amount of temperature change that we've had. So in other words, the temperature change is progressing pretty strongly, and it's impacting the climate and the Earth, and particularly the human systems, stronger than we thought it would. So we combine that calibration with modeling, climate models. And this question of climate models is also often a little bit confusing. So the first thing I want to point out is that these are not the models that are helping us better understand Earth's climate system. I've never once seen them in the lab. In this case, models simply means physics. And not climate physics, just plain old physics, the exact same physics that allows us to build microwave ovens, smartphones, digital cameras that we place on spacecraft, that we send to the edge of our solar system to take pictures of our own planet and send back to us. Just applying that physics that we know very well to the climate system is what we mean by these models. And these models then allow us to make projections. How much more warming and subsequent climate change can we expect in the coming decades? And so what I'm going to do is show you a few projections of this. You've seen, this is just a plot of the global temperature record I showed you earlier. Here I'm using a line instead of bars. And what I'm going to do is squish it down to give me some more room on the temperature scale, and then squish it down again to give me some more room on the time scale, and take us out to the end of this century. And so here's the observations up through the year 2010 smoothed out to get rid of that short-term noise. You can see climate change right there, global warming. And then here's the spread of projections from this modeling. We're going to use 1990 as our baseline in this case. So at the point of 1990, we had already warmed about 6 or 7/10 of about 6/10 of a degree relative to pre-industrial temperatures. And then here's the spread of the modeling going forward by the year 2100. So looking for over 1990 temperatures, an additional 1 degree Celsius to perhaps as much as an additional 4.5 or 5 degrees Celsius of warming on top of the 6/10 you already had right here in 1990. And you might look at that and say, well, that's quite a spread. That's pretty uncertain. Those models don't seem very good to me. And it's certainly true that we don't know everything about the climate system, and we don't understand the physics perfectly. That said, I'll say that not knowing everything is not the same as not knowing anything. We do know quite a bit. But that's not the major source of our uncertainty. There's a little bit of uncertainty just due to natural variability. Some years are a little bit warmer, a little bit colder due to things like El Nino. There's some more uncertainty because we don't understand the physics of the climate system perfectly, but most of this uncertainty is because we don't know how we humans will choose to move forward in the coming decades. And so we have to project for different scenarios. And specifically, the different scenarios are a low carbon emission scenario, lower emissions, which give projections in the lower end of an additional 1 to 2 degrees Celsius of warming by the end of the century, to the higher carbon emission scenarios, which is the scenario we're currently tracking on, which gives us these higher projections by the end of the century. It's worth pointing out as well that there's some significant difference between sort of qualitatively as well between these two scenarios. On the lower scenario emissions, you see by the latter half of the century we're starting to level off in temperature rise and even start to come down just a little bit, assuming we've moved heavily away from dumping carbon into the atmosphere. On the higher scenarios, though, the higher emission scenarios, you see it's a qualitatively very different behavior on the graph. It's not leveling off by the end of the century. We just cut off the simulation. The warming continues into the 22nd and 23rd centuries. And this is already some pretty extreme warning. So the difference here is what we choose to do. That's the biggest source of uncertainty in the projections. Let me put that in a slightly different context here, maybe just more schematically for you to look at. This is a thermometer graduated in Fahrenheit, you're welcome, 45 degrees Fahrenheit on the left. The global average temperature at the depth of the last ice age, 15 or 20,000 years ago. 75 degrees Fahrenheit, sorry you can't see that very well. This is 75 degrees Fahrenheit on the right. The warmest we think the planet's ever been, about 55 million years ago. Now humans show up on the scene, anthropologists tell us, about 200,000 years ago. And so that's the green oval. That's where the human ecosystem and human civilization evolved. And in particular, so this is where we have always lived, in that green oval. And in particular, between the two lines is where human civilization arose and has always existed. That's the climate of human civilization. Okay? This climate has been very stable. It's called the Holocene by the geologists, and is defined by a very stable climate over the last 15 or 20,000 years. This blue oval here is the projections I showed you before in Fahrenheit out to what's called a 95% confidence level of where we're headed this century. And you'll notice that there's no piece of those two ovals that overlap. So in other words, and a number of scientists have made this analogy, it's like we're moving to a new planet. We're moving to a climate that humans have never, ever known. And we're doing it pretty quickly. That said, there's a big difference between the low end of an additional 3 degrees Fahrenheit global average temperature rise, which is still quite significant, to an additional, say, 14 degrees by the end of this century. Okay. It's just not the human climate. So this is the scale of the change that we are facing this century on the trajectory that we're currently on. Let me just show you some more regional projections of temperature in North America under these two different scenarios. This is the end of the century under a low emissions scenario, an additional 4 degrees Fahrenheit or so for Utah. This is the end of the century under a high emissions scenario, an additional 13 degrees Fahrenheit for Utah. So those are the two different spreads. And I'll point out that the Arctic is warmed under a high emissions scenario about 25 degrees Fahrenheit. This is just extreme climate change. Here in Utah, snowpack is very important, particularly springtime snowpack. This is when the snowpack is typically at its deepest and then starts to melt and fill the reservoirs, and we use it in our homes and in our cities and for agriculture. I want to show you how the snowpack is projected to evolve under a high emission scenario. So here's the snowpack over the Rockies. The colors are a little washed out here though, but the darker colors there are the deeper snow, and the lighter colors are the thinner snowpack. And what I'm going to show you first is some data as to how that snowpack has been over the last 50 or 60 years or so. So actual observations of the springtime snow depth over the Rockies. We're going to start in 1950, and then I'm going to show you some projections taking us to the end of the century. So as we move forward, the observations show us that it's variable. Some years are snowier than others. We all know that. By the 1980s, the variability starts to increase, and now we're into projections. And as we warm, not surprisingly, we see a thinning snowpack through the middle of the century. By the latter half of the century, we essentially see no springtime snowpack. Again, this is under a high emission scenario. That's the scenario we're currently tracking on. Also important, of course, to human civilization, certainly to us here in the West and in Utah, is soil moisture. What goes into these projections is not only temperature, is not only precipitation, but also temperature. So you can actually have some kind of a perverse situation where you might even get moderately increased precipitation in a particular location, but end up with a drier soil. That's because the evaporation has also gone up because the temperature is rising so much. Okay? So that's what goes into these. Here's a moderate emissions projection for this century. As it turns brown, that's drying. And you see significant drying through the middle of the century, more drying towards the end of the century as well, but not quite as fast. That's sort of assuming under this moderate emissions scenario, we've kind of gotten religion somewhat, somewhere in here, and gotten our act together with emissions. Now we'll look at that under a high emissions scenario through the first half of this century, and then the latter half of this century. Now, I haven't given you actual numbers, and you'll notice Alaska and northern Canada up there actually get wetter. That's what the blue means up there. I haven't actually given you numbers to try to interpret this. I'm just going to tell you that the agronomists, the economists, the social scientists, and ecologists who study these scenarios will characterize the low emissions or the moderate emissions scenario as dangerous for human civilization, for our human society, and the high emissions scenario as catastrophic. That's the words that the people who analyze these use. So, rising temperatures, declining snowpack, intensified hydrologic cycle, and significant, huge changes to soil moisture, things like that. Just some of the impacts that we're looking at, and how do you interpret this though? I mean, so how do you, I want to just give you a sense of what the scientists themselves are saying. I've got quotes from two scientists. The first one is Lonnie Thompson, quite a distinguished glaciologist. Virtually all climatologists are now convinced global warming poses a clear and present danger to civilization. I agree with that. I concur with that. That's my experience in reading the papers, the scientific literature, and the public comments. This is the mainstream scientific opinion, unquestionably. I can find scores and scores of such quotes like this one. Kevin Anderson is quite a distinguished carbon modeler in the UK. A widespread view that a 4C future is incompatible with an organized global community. What he means by 4C future is a globe that has warmed 4 degrees Celsius over pre-industrial temperatures. We've already warmed 1 degree Celsius. Okay? Is likely to go beyond adaptation, devastating to the majority of ecosystems, and a high likelihood of not being stable. What he means by that is the climate system is complex. It's kind of twitchy. It's what we call a nonlinear system. So it means it doesn't respond equally to equal perturbation. So you can kick it a little and it changes maybe a little and relaxes back to where it was. You can kick it a little, it changes a little. But if you kick it a little more, it can flip into a completely new state and change a lot. And then And we understand that this is the dynamics of the climate system. So there are tipping points. At this point, based on studying past climates of the distant past, we believe those tipping points are somewhere between a 2 degree and a 4 degree temperature rise, Celsius. And so once you pass a tipping point, then you're going to change, and there's kind of nothing you can do at that point to stop it. You're going to just, the ball is going to roll to a new place, and it's going to sit there in a very different climate state. So these quotes may sound kind of shrill, not compatible with an organized global community, clear and present danger, but I'll just tell you this is the mainstream scientific opinion at this point of the scale of the risk that we are facing on our current trajectory. So Earth is warming, principally due to us, principally from the burning of fossil fuels. This warming is disrupting the entire climate system, and if we continue, it poses extreme risks for humans. And I never get invited to parties anymore. This brings up the question, though, but that's just the straight poop. That's where we are. The science also has something to say about how we mitigate this. And I forgot to say something when we were looking at those projections before. There's some good news in this. And the good news is the change in front of us, based on the physics, based on the modeling, is mostly up to us. The biggest spread is from high carbon versus low carbon scenario. So it's still up to us. We are actively choosing every day which path to take as a society. So what does the physics have to say about mitigating this risk if we really want to choose that low emissions path? So internationally, 193 countries have agreed that our goal is to prevent dangerous human-caused disruption of the climate system. That's great. We need to translate that into physics. And the way that we've done that is to say that we want to hold the increase to well below 2 degrees Celsius of warming above pre-industrial temperatures. It's even better if we can hold it to 1.5 degrees Celsius, and we've already warmed 1 degree. Okay? So there's our goal. Given this goal, physics can calculate how much more carbon can we dump into the atmosphere and expect a reasonable chance of staying below this 2 degree or 1.5 degree line. And the equation is this: more carbon equals more risk. We're going to set a danger line at 2 degrees Celsius, maybe even 1.5 degrees Celsius, and we'll calculate a carbon budget. And here's that budget: 1,000 units of carbon dioxide, gigatons are the units. 1,000 more we can dump into the atmosphere. And it doesn't matter when we do it. We could do it all next year. We could take 50 years or 100 years to do it. But if we dump this much more in, we can expect a lower chance of staying below 2 degrees Celsius. But this calculation was done in 2010. It was a very big modeling effort all around the world, running lots and lots of simulations and then doing what are called ensemble modeling averages to come up with this number. But that was done in 2010. Since then, we've chewed up some of that budget. So that's what we've got as of essentially today. And this is how fast we are going to chew through that budget absent meaningful change from the way we produce and consume energy. About 2 decades. Here's that budget relative to our known carbon reserves. This is coal and oil and natural gas that we already have found and we know how to dig up. So what the physics is telling us is if we want to engage in serious risk management, we can only burn about 1/3 of our carbon reserves. This number is roughly 3 times our budget. Now that's not including non-traditional recovery methods such as fracking and tar sands recoveries. But we have been fracking and we have been mining tar sands, so we should probably include those reserves as well. And if we do, the physics is telling us we can only burn 1/8 of our budget if we want to mitigate this change, if we want to engage in serious risk management. Okay, so to summarize very succinctly then, dangerous climate disruption is underway currently. Catastrophic climate disruption is likely currently on our current track by the end of this century, and we have about a 2-decade window to turn that around. Beyond which you put things in motion that are very difficult to reverse. Right, so is that the end? Fortunately not. We have a mountain to climb, and there are many strategies for reducing our carbon emissions globally. The world's nations are now talking about those strategies very seriously. And so the question is how to move forward. What I'm going to show you right now is a roadmap of one way forward, and the criteria for choosing this particular roadmap that I've used is this is technology that we already have. These are things that we already know how to do. It's not fantasy, it's not theoretical, and doesn't involve things that we need to invent that we don't have. And so the roadmap is really just two pieces: changing the way that we consume energy, it's called demand side in the biz, and changing the way that we produce energy. It's called supply side transformation. Let's start with the demand side. Essentially, because the time is short, we need to make deep energy reductions in the way that we consume energy. And it turns out that you can actually make pretty significant progress on this in our homes and in our factories with efficiencies. And to illustrate that, let me just tell you that in order to get 10 units worth of useful work from our electricity in our homes, so 10 units worth of light produced or heat produced in your toaster, the power grid needs to deliver to your home 50 units of energy. That's because the appliances, all the things we use, are very inefficient. An incandescent light bulb turns about 2% of the energy you feed into it into light. The rest of it is heat. LEDs are much better. So that's one way to achieve, to move towards this efficiency. But in order to deliver 50 units of energy to your home, the grid has to deliver 54 units to the corner outside your home, where the transformer takes it to a lower voltage and puts it in your home, because there's some loss in that process as well. And in order to deliver 54 units to your corner, the grid has to start out with 120 units at the power plant that's fed into the grid, because there's a lot of loss as you transmit it, hundreds of miles. And in order to put 120 units into the grid, you actually have to burn 133 units of, say, coal to get this process started. But what this tells us is, if we can reduce 10 units worth of energy in our home, for every unit of energy we reduce in our home, we reduce the demand for 13 times that much energy. So it can make a very big difference if we decide not to use energy or to use energy much more efficiently in our homes and in our factories. That's then the demand side. And it's also important to note here that this isn't something that everyone on the planet needs to do. About 10% of the world's population produce 50% of our carbon emissions. 20% produce 80% of our carbon emissions. This is very much a task for the developed world. And that's those of us in this room. And there's no question about it. There's no way around that. We're the ones that are consuming the energy at an extraordinary rate. And so we're the one, this is where the biggest savings are to occur, is in the developed world. So that's the demand side, the deep energy reductions. Let's look at the supply side. How can we change the way we produce energy? And that's through a massive deployment of zero carbon technologies. To give you an example, in the first 3 months of this year, the United States installed new electrical generation that was renewable, that's mostly solar and wind, some hydro, this is dams, but mostly solar and wind. We installed about 1,300 megawatts of new electrical generation in this country in the first 3 months of this year. That's enough to power about 250,000 homes. In that same time period, we produced 18 megawatts of new natural gas. So the renewable is low carbon, the natural gas is high carbon. And in that same time period, a whopping 0 megawatts of new coal and oil. And I've included nuclear on there as well. But the point is, from this graph, we clearly know how to do this. We just need to do it at a greatly accelerated pace. It is not a question of research and development, it is a question of deployment of this technology. We know how to do it. I'm not saying it's going to be easy, it's a massive deployment, but there is precedent for this kind of a transformation in our past. Around the world, Portugal powered itself this year for 4 days straight in May with 100% renewable energy. It's not quite fair. Portugal has quite a bit of hydropower. Nevertheless, they've done it, and they've done it several times since. Germany, the world's 6th largest economy, powered themselves 90% renewably on 1 day in May. They've done it several days since. This is mostly solar and wind. And I don't know how many of you have been to Germany. I've been there 3 times, and I'm pretty sure I've never seen the sun in that country. Great Britain ran without coal for a week this year for the first time in 130 years. And they've done it several times since as well. And these are very strong economies. Germany in particular. California is another example. So the notion that, that in order to do this, it needs to be economically disastrous is demonstrably false. There's no question that it could be done economically disastrously, just like you could hire a really crappy roofer to build your roof. But it doesn't mean you have to. There's good roofers out there as well. So we have models to follow. This is doable. So there's the roadmap. Demand side, deep energy reductions on our consumption side, massive zero carbon deployment is what is needed in order to meet this timescale of about 2 decades. So in addition to these 4 things that we know about climate and climate change, we know something more, and that is that we already have what it is we need to mitigate, to choose a different path moving forward. I'm going to end with just a couple of, we've already seen this, yay. I want to end with just a couple of quotes that I'm going to read to you. This is Dennis Meadows, who's some of you may have heard of, one of the principal authors of a book called The Limits to Growth in the 1970s, an extremely well-accomplished complex systems modeler that's looked at these interfaces of human and environmental systems. In addition to saying, I think this great quote here, yet another response to the notion that we can't economically make this deployment, we are going to change the way we do things. Those changes will either be imposed upon us in the next several decades by an Earth system that can no longer keep up with us, that's just going to change it, or we can try to engineer our way into a softer landing. Often is the question, what can I do? Here's what Dennis Meadows says. There are many things to do to bring about a sustainable world. New farming methods have to be worked out, new businesses have to be started, and old ones redesigned. Land has to be restored, parks protected, energy systems transformed, international agreements reached, laws have to be passed and others repealed. Children have to be taught, so do adults. Films have to be made, music played, books published, websites established, people counseled, groups led, subsidies removed, sustainability indicators developed, prices corrected to portray full costs. All people will find their own best role in all this doing. What he's saying here is, if you're a student, you don't have to change your major to environmental science to impact these issues. And if you're an adult, you don't have to change your profession. This topic affects all pieces of our human endeavor, and therefore all pieces of our human endeavor have a contribution to make in turning the ship systemically. The changes we need are systemic. And so I'm simply going to throw that out there and leave you to go maybe do a little bit of research. I'll recommend 2 people to look at, and I forgot to put it up here, so ask me again if you don't get this. One is Johan Rockström, has a fabulous web TED Talk called Planetary Boundaries. Kate Rayworth has a fabulous TED Talk called Donut Economics that address some of these topics that you can learn further from. And there's one more quote that I want to end with. Anybody know who that is? No. Good guess, though. Oh, Bernard Shaw. Yes. This is George Bernard Shaw. I love this quote. I wish I could do a voice. I'm just not an actor. This is the true joy in life. The being used for a purpose recognized by yourself as a mighty one. The being a force of nature instead of a feverish, selfish little clod of ailments and grievances complaining that the world will not devote itself to making you happy. I am of the opinion that my life belongs to the whole community, and as long as I live, it is my privilege to do for it whatever I can. I want to be thoroughly used up when I die, for the harder I work, the more I live. I rejoice in life for its own sake. Life is no brief candle for me. It is a sort of splendid torch which I have got hold of for the moment and want to make it burn as brightly as possible before handing it on to future generations. I take this to mean the following for me, and we can come away from this information, and maybe we can have the lights. Thanks, Doug. We can come away from this information feeling depressed and in despair and feeling like it's hopeless. I'll simply say that I understand that feeling, and I have my moments, but the notion of whether or not we can turn this ship or not, the question of whether or not it can be done, is not a useful question. It's an unanswerable question. There's no calculation we can do. There's no analysis we can make that can say, yes, this is doable, or no, this is not. We just don't know at this point. There's too much uncertainty. So to my mind, and what Mr. Shaw is essentially alluding to, is this notion is, if you can identify a next step that appears to be meaningful, then I think our job is to take it and not worry about how it plays out. If there's a next step, we take it. And I think that's the way that we make if there is a way to navigate this, that's the way that we do it. So thanks very much for your attention, and I'll turn it back over to Doug.